Assalamualaikum warahmatullahi wabarakatuh. Can you hear me?
Yes, Doctor.
Bismillahirrahmanirrahim. Good morning. So we continue our lecture today, remaining 1 hour, by looking at the rule of locus theory, rule number 7. Okay. So the rule number 7, the theory is the imaginary axis crossing. Okay. Imaginary, which is this one. This is imaginary. And this is the real axis. Rule twist can be used to find the crossing of the rule locus. Okay, so this is your asymptote line. This is your rule locus line. So this crossing intersections between the rule locus and the imaginary axis can be calculated using a rule twist method. Okay, so the imaginary axis or j omega axis crossing is a point on the rule locus that separate the stable and unstable operations. As we know that left half plane is the stable part, right half plane is unstable, and on the top of imaginary axis is the marginal or critical. Okay. So you use the RH criterion to find the point of that particular intersections. So if you still remember, you learned the theory last semester, which is the Routh-Lewis table. If you have the block diagram and the transfer function given by these equations. Okay, so we are only interested on the bottom one, which is known as the characteristic equations. Okay, the closed loop denominator of the transfer functions equal to 0. So this is what we call as the characteristic equations. And our concern is on the coefficients A4, A3, A2, A1, and A0. So we plug in A4, A3, A2, A1, A0. And then the remaining we insert as 0. Okay. Then we continue the fill up until at the bottom. Okay. So this is what I call as determinant. Okay. Determinant of A4, A2, A3, and A1. Okay. So is a cross multiplications. A4, A1 minus A2, A3. Okay. And the rest is still the same. You just follow this table guidance, okay, the completed Routh table. So 0 in the first column, it is two special cases for Routh-Lewis, which is 0 in the first column. Okay, so if you find a 0 in the first column, okay, so like this, you replace with the one variable with known as epsilon. Okay, this is epsilon symbol. Okay, for example, for this closed loop transfer functions, it have zeros in the first column. So this is the first column. While in another cases where you have these transfer functions, right? So it will produce a row of zeros, which is at S cubic. Okay, over here. So if you see this kind of special case number 2, where the entire row is 0, so you will get a this kind of method where you have to find the auxiliary equations, which is s power of 4 plus 6s2 plus 8, okay, from here, 6. Okay. Then you differentiate it, okay, you differentiate it, and then you solve the problem for row of zeros, which is 4, 12, and 0. You insert inside the next line, the next row of the Rolf list. For example, if you have this example 6, slides 54, okay. So you're required to find the frequency and gain, okay, K, for which the root locus cross the imaginary axis, for what range of K the system is stable. Okay, so you are required to find the frequency and gain. Okay, so the frequency will be omega n and gain K, for which the root locus cross the imaginary axis. Then you have to find the range of K. Okay, minimum, maximum. Okay, so you are given the open loop transfer functions, which is this one, and determine the closed loop transfer functions as the first step. But we have to identify the zeros is -3, the poles are at 0, -1, -2, and -4. So it's the fourth order. Okay. Fourth order. Okay. So how are we going to find the closed loop transfer functions? Raja Ahmad Zahid. How are we going to find the closed loop transfer functions? Tak datang. Raja Ahmad Zahid. Datang. Sadanan sakit.
Yes, doctor.
How are you going to find the closed loop transfer functions?
Doctor, it would be like yes. So now it would be g of s divided by 1 plus g of s. That is k into s plus 3.
So k s plus 3 1
divided by
plus s plus 2 s plus 4.
Yes, doctor.
Correct? Is this correct?
Doctor, 1 should be like
G
divided by 1 plus g of
yes.
yes.
So meaning that this one need to be added.
Added, yes, doctor.
By s plus 3. Okay.
Yes, doctor.
So at the end of the day, so you akan dapat macam ni lah. Okay. TS sama dengan K S plus 3 Okay. K S plus 3 over S4 7S3 cubic plus 14S squared 8 plus KS plus 3K. So what is the characteristic equations for these closed loop transfer functions? Abdul Ghani Said.
Yes, doctor.
What is characteristic equations?
The one is in the below.
No, 1
It's the
S for 4, 7 S cubic, 14 S square, 8 plus K
plus AK S plus 3K.
equal to 0. Eh? So that
Yes.
closed loop transfer functions. So you insert the value 1, 7, 14, 8 plus K, 3K, and this one automatically 0. Okay. So then you continue the fill up. So you will get 90 minus K, 21K. Then continue fill up minus K square minus 65K plus 720 over 90 plus K and 21K. Okay. So row of zeros yield the possibility for the imaginary axis pole. Row of zeros. Okay. So row of zeros, you see that the equations now become minus K square minus 65K plus 720. So which is can be written like this, minus K square from column 1. Okay, so you see that minus K square minus 65K plus 720 over over 90 minus K. Okay, for stability must be greater than 0.
It's 90 minus K.
90, 90 minus K, sorry. So simplify, minus K square 65K plus 720 greater than 0. Okay, so find the value of K. What is the value of K? So the value of K will be, have two values, isn't it?
Yes, doctor. 9.645 and negative 74.645.
I'm using a MATLAB, so I fill up the polynomials here and then find the roots. So minus 74.64 and minus 9.64 minus, sorry, plus 9.64. So which one is the positive number? This one, okay? This one is the positive number. So this one disqualified, okay? Disqualified due to it is a negative number. So K is 9.64. So that's why, okay, 9.64 or 9.65, the range will be 0, K, 9.65. So the range.
Doctor, why the negative value is disqualified?
Because here we take all the from the first column, okay, from the column 1, okay, column 1 is here, in the notes. Yeah. So this is column 1. 1 positive number, 7 positive number, 90 minus k or greater than 0 positive number, minus k square all equal more than 0 positive number, 21k more than 0 positive number. So in order to be stable, okay, in order to be stable, the first column must be greater than 0, okay, greater than 0, like this, must be greater than 0, okay. So that's why minus 74 is not included, only plus 9.64, because when you insert this minus 74.64 inside these equations, you will not get greater than 0, okay. Faham tak?
Doktor,
Yes.
kalau row 1 dengan row 2 tu memang negatif.
Row 1 saja, kita tak pakai row 2. The theory said for stability, column 1 must be greater than 0.
What about the other column, 2 and 3?
No, column 2 and 3 is not included in the theory, only column number 1. Okay.
Doctor, sorry for interrupt.
Yeah.
Can I ask why the column 1 the S0 not using, but we use the S1?
Come again?
I don't understand because in the column 1 still got the S0, right? The 21K.
Column 1.
Yeah. I'm not sure why we need to choose the negative K square minus 55K blah blah blah. Other than the 21K.
Other than 1, okay. Your question is, I don't understand your questions. Because we have to find the range.
S1. Now we are using the S1 to find the root, right?
Yeah.
Then I'm not sure why we need to use S1 but not the S0.
Okay, let's see the column 1. What is the column 1? The first one. The first one. The first one. 1, isn't it? Is it 1? Is it 1?
Yes, 1.
Greater than 0?
No. What I mean is for the equation is from S1, right? S1. Got S4 until S0, right?
Yeah.
S4 come to S0.
Yeah.
Then why we need to use the equation inside the S1 but not the S0, because S0 is the last one we find out, right?
Okay.
Why we need to use the S1?
Okay. Why you don't want to use? Why we don't use 21K? Why we don't use?
Yeah. This is my question.
21K, from the last row, isn't it? Okay. Easy. So I got it. Greater than 0. K greater than 0. Am I right? If you simplify this, you will get this. Am I right?
Yes.
Yes.
Greater than 0 lah. Kan? Jadi, yang in this one, 1 is already greater than 0. 7 greater than 0. Then 90 minus K greater than 0.
Okay, I understand.
But,
yeah.
90 minus K greater than 0. Minus K greater than minus 90. Then I use magic, I use magic. Change sign. Am I right?
Yeah, understand.
So it's a basic mathematics lah. Right. So the range will be 0. The range of K for stability will be 0, K, then less than 9.64. But in the notes, 9.65, more or less is the same. So if K is equal to 9.64, So this one meaning that the system is marginal, critical. Okay, 9.63 still stable, 9.639 still stable. But when it is equal to 9.64, the system become K critical or marginal. Okay. So forming the even polynomials with K 9.65, which is this one, this polynomial, okay, which is 90 minus K S square plus 21K. So you insert the value of 9.65 inside this one. Okay, so you will get 90, this one 90 minus 9.65. You insert the value 21K and you will get 80.35 S square plus 202.7 equal to 0. Okay, then you simplify this. Okay, so you will get S is equal to plus minus J 1.59. So 1.59 is the root locus intersection with imaginary axis. Okay, but since the imaginary axis is plus J omega plus J 1.59, so automatically the frequency will be 1.59 radian per second. Okay. There you go.
So forming the even polynomial is fixed one, right?
Yeah, because we have a case of row of zeros in these transfer functions. That's why we use the polynomials, the even polynomials. Okay. Any questions? Okay. Next one will be the root locus procedure for rule number 8, which is the angle of departures and angle of arrivals. So angle of departure, which is pole, and angles of arrivals due to zeros. Okay. Angle of departure due to the pole and angle of arrival due to 0. This is the like a aeroplane concept now. Depart and then pole and then arrival. Okay, can be calculated to further refine the sketch. So use for complex open loop poles and complex open loop zeros. Okay, so in this case, angle of departure due to the complex pole and angle of arrival due to complex conjugate zeros. Okay, so the root locus depart from the complex open loop poles and arrives at the complex open loop zeros. And the angles can be found using the angle property, which is theta A. Theta A is the summations of angle of all poles to B minus angles of all zeros to B plus 180 degrees, while theta departure is summation of angle of all zeros to A minus the angle of all poles to A plus 180 degrees. Okay, so this is the diagram. The statement said A and B is here because of the diagram A and B. Okay, so angle of departure due to the complex conjugate poles, which is here. Okay, so the angle of departure is theta 1 plus theta 2 plus theta 3. This is due to the zeros. Okay, minus theta 4 minus theta 5 plus theta 6. This is due to the poles. Okay. Equal to 2k plus 1, 180 degrees. Okay. So for the angle of arrivals at B, okay, so we have theta 1 minus theta 1 plus theta 2 plus theta 3. Okay, this is due to the poles. Okay. And theta 4, theta 5, and theta 6, which is equal to the zeros, okay, as shown in the diagram. Example 7. So for the unity feedback systems, find the angle of departure from the complex poles and sketch the root locus. So theta d, you have to find the theta d. So if you look at this transfer functions, the zeros is -2, the poles is at -3, and this is a complex conjugate poles. Complex conjugate poles. So what is the roots for this? S square plus 2s plus 2. Helpful.
It's got -1 plus I or -1 plus J and -1 minus J.
J1. Right. J1. So as shown here. Okay. And then we have poles at -3, which is here. And then we have zeros at -2, which is here. So theta 1 and theta 2 is the angles due to the complex conjugate poles. Theta 4 due to the poles at -3, angle due to the poles at -3, and theta 3 is the angle due to zeros at -2. So therefore, theta 1, okay, is equal to summation angles for all zeros to the poles minus summation angles of poles to the poles plus 180 degrees. So theta 1 equal to theta 3 plus theta 2 plus theta 4 plus 180 degrees. And that's why theta 1 is equal to 108.4, the angle of departure, okay, which is theta d. Okay. Theta 1 itu adalah theta d. And then rule number 9 is plotting and calibrating the root locus. So all points on the root locus satisfy the magnitude and angle of properties. So we may want to locate on the root locus and their gains, for example, and the root locus crosses the line representing 20% overshoots. Okay, so this one is will give you another value of zeta. Okay, because once you know the overshoots, you know the zeta values, and the gain at any point on the root locus is given by k, okay, 1 over g h, which is magnitude, or 1 over m, product of finite pole length divided by product of finite zero length. Okay, but for this one, overshoots, usually we can calculate the zeta based on the formula or based on the graph, standard graph. Okay, if you still remember the graph, like this. And so that is the standard graph for the overshoots versus example 8. So for a unity feedback system that has the forward transfer functions, okay, k multiplied by s plus 2 divided by s square minus 4s plus 13. So do the following, which is the sketch the root locus, find the imaginary axis crossings, find the gain at j omega axis crossings, find the break-in point, find the angle of departure from the complex poles, and then verify using Maxwell. Okay. So we do it manually first. Okay. So k s plus 2 s cubic minus 4s plus 13. So the open loop zeros is minus 2. The open loop poles is 2 plus J3, 2 minus J3. Okay. So the poles located on the right half plane. Okay. Okay. Then zeros at minus 2. Okay. So as we know that rule occurs, the path start from poles. Okay, start from poles and ended at zeros or infinity. So in this case, the rule occurs will met at the break-in point. Okay, and then they left from the break-in point. One goes to the zero, ended at zero, and the other one ended at infinity. Okay, ended at infinity. So that is a break-in point. Okay. So using the Roth-Roos criteria, okay, first we find the closed loop transfer functions, okay, from the open loop. So this is your open loop transfer functions. Then from the open loop, we find the closed loop, which is 1 over 1 plus g. Then we obtain these equations, okay. And then from the closed loop transfer functions, the bottom or the denominator is under our concern, where the then polynomial must equal to 0, which will give you the characteristics equations. So the characteristic equations is s squared plus k minus 4 s plus 2k plus 13. Okay, so this is the coefficients 1, k minus 4, and 2k plus 13. So you insert inside the Roth-Roos. Okay. Then continue the fill up until S0. So you will get 2k plus 13. Okay, 2k plus 13. Then use the equations s squared plus 2k plus 13 from the first row, okay, equal to 0, where k is equal to 4. So s squared plus 21, so you will get the value of k is square root 21. Square root 21 is 4.58 radian per second, meaning that this is s is equal to plus minus j 4.58. Okay. So the omega n will be 4.58 radian per second. Okay. And the gain k will be 4. K critical, okay, is equal to 4, where the root locus cross the imaginary axis. Okay. So searching for the minimum gain to the left of minus 2 on the real axis. So minus 7 and a gain of 18, thus the break-in point is minus 7.
بيشرحش الخطوات بالتفاصيل بيجيب لك الفورمولا وبيديك على طول
Off microphone, Hassan. Minus 7. So you can calculate the break-in point by using the d per ds as well, okay, to verify the value of minus 7 like this. Okay, so this is the open loop transfer functions. Okay, so it's equal to u divided by v. Okay, so if you want to differentiate, so you have to use the concept of v du minus u dv divided by v squared. So simplify, so you get this value, you get this quadratic equations, and you get the value is minus 7 and 3. So which one will be the break-in point? Which one? We have two values. Okay. So definitely positive 3 is disqualified because positive 3 is over here. And so the more reasonable is this one, which is -7. Okay, it happens at the -7 for the break-in point. Okay, and then what is the value of the break-in point? So the value of the break-in point, which is -7 over here. So we have to calculate the length, L1, L2, and L3. So the zeros located at -2. Yeah. This one is complex conjugate poles is minus 2 plus minus J3. This one, 2 plus J3. And this one, 2 minus J3. Okay. So what is the length for L2? Directly from here, the length will be 5. Am I right? Am I right, Safwan? The length. Safwan, Ido. Luqmanul Hakim. Luqmanul Hakim. Also tidur. Abdul Rahman Syarudin.
Yes, Doctor.
Betul tak 5? Is it correct?
Yes, Doctor.
Okay. Then length 1. What is the length 1? L1.
9.
Square root 7, 9 square plus
3 square.
this one also same. So L1 and L3 is the same. So what is the value of L1 and L3?
9.487.
9.4.
487.
Okay. So that's why the L1 multiplied by L3, 9.487 square divided by 5. So you get the value of gain K at the break-in point as 18. Okay, 18. Then for the angle of departure, first draw the vectors to a point of epsilon close to the complex poles. Okay, your complex poles is here. 2 plus minus J3. Then at the point of Z epsilon, close to the complex pole, the angle must add up to the zeros. Hence, angle from zeros minus angle for the pole in the fourth quadrant minus angle from the pole in the first quadrant equal to 180 degrees. So the theta departure is arctangent 3/4 minus 90 minus theta plus 180 darjah. So you will get minus 233.1 for the theta departure. Then we plot, okay. So we plot here, this is your zeros, this is your complex conjugate poles, and this is your 7, which is the break-in point, okay. And by using MATLAB, so we can obtain that the damping over here is 1, okay, and over here is minus 0.507. Okay, the pulse is located on the right-hand side. So the theory says that this is unstable. So example 9, all right, example 9, we stop here. We stop here for lunch, 12:40, okay. So I will continue this next week, inshallah. Any questions?
Doctor, can you like go back to example 8? I want to ask about so go back one more time, go back. This one, the angle is, yeah, this, sorry. So one slide after this. So next slide. I want to ask about the 180 degree. Is it always going to be 180 degree for finding?
Yeah, the formula is 180 degrees.
Okay, so it won't be like multiple of 180, like 540 or no, it's always 180, is it?
Yeah.
Okay. Thank you.
Angle of departure. Angle of departure due to the complex conjugate poles, angle of arrivals due to the complex conjugate zeros. Any question, Arab brothers?
Thank you so much, Doctor.
Any question?
Yes, Doctor.
Very quiet today.
Doctor,
Yes, please.
can I ask something in the rule 7?
In the rule. Sorry?
I don't know something inside the rule 7, the 7 rule.
7 rules. 7 rules. Okay. Oh, rules of 7. The intersection between the root locus and imaginary axis.
Yes.
Yeah, what?
I don't understand, like, because the forming the even polynomial, right? Then where's the S4 power of S? S to power of 4. Because there is also 1, right? At the part of the S power of 4.
Yeah.
But then inside the under there don't have the S4. So I don't know if is it missing or what, or not. Don't need to include.
Not missing. It's not missing. Is a row of zeros occurred at the rows here. Yeah. There is a row of zeros. It's not missing. Okay. So the theory of the row of zeros is here. This is a row of zeros. Okay. So when there is row of zeros happen, okay, for example, S power of 3 n. Okay. So you need to take the auxiliary equations above it. Okay. S power of 4 here. S power of 4, 6s squared plus 8, then you differentiate, then you insert this value inside the row of zeros. So it happened here as well. It's not missing. It's a row of zeros. You have to take the above polynomials, then you differentiate, then the coefficient of the differentiate you insert inside the S power of 1. Did I answer your questions? Further readings, you can read from the Norman Nice book chapter. All right? There is an explanation of it in the Norman Nice book chapter. Who's asking the question? Low, eh? Siapa yang tanya soalan?
Tio.
Huh? Low.
Tio.
Tio. Okay then. So I see you next week, inshallah. Okay. So have a nice weekend and see you next week. Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
All right.